Welcome to the week 9 of the course. We have discussed various aspects of the computer aided decision support systems and some case studies on big data analytics, how is it supporting the computer aided decision support systems in a way. Professor Deepu Philip has covered a few basic languages, and also he will try to cover HTML in the coming weeks. That is a markup language that you need to understand to finally display what you have understood in the previous weeks. I have discussed in the week section majorly the decision support systems for the computer aided design and computer aided manufacturing. Majorly the focus was on computer aided design in the last week. I have discussed the geometric shapes, what are the geometric shapes, what are different kinds of the geometric modeling features that we have, what types of geometric modeling. We shed a light on the surface modeling, wireframe models and the solid modeling, the different applications and uses of them. How is computer aided design supported by the different libraries that we also try to see using the CNN, the convolutional neural network system, where the different shapes are there and the kind of the object that you are trying to replicate that could be taken from different library shapes, and you can identify the specific shape while classifying and matching with the existing one, and you can set into a specific class and try to take the features of that class and start to develop the model from there. This is how big data analytics has helped us to have a more closer information or understanding of the drawings that we are trying to develop. That means the people who are not from the manufacturing or the CAD/CAM background can also start their own designs. Yes, final vetting is to be taken by the engineer who is a CAD engineer. That person would help us to have the proper tolerancing, and that would be definitely supporting you. This week would be more focused on the decision support systems in computer aided manufacturing. Since we discussed about the neutral files or the product data exchange in the last week, and also we understood that the post processor is the one that communicates with the machine tools finally. But yes, there are many other things that are still needed to be discussed, because the decisions that are to be taken or to be communicated to the machine tools requires certain steps in between. That is why I have designed this lecture to understand first thing is the process planning. What is the process planning? Like we discussed about the assembly planning or assembly tree in the last week. Assembly tree is just like a decision tree as we see in the last week. Similarly, there are certain other decisions that are to be taken, certain other formats to be made which happens in the process planning. Assembly planning is one of the only parts of the process planning. Then comes the part programming. Part programming is one when you have the geometrical dimensions and then you try to now have a program on them so that you can finally execute them for the manufacturing. So, that is part programming, in which we will also see how do we integrate CAD and CAM, what are the different steps or different languages in it, in which we will see different decision support systems for the computer numerical control machines. We will start from the NC only, that is the numerical control. The final communication is taken by the different code systems. This is one of the system, that is the G code and M code, that also will put some light on. Process planning. Process planning as a term itself is planning of the process, which means that the steps that you are going to execute for the manufacturing, that you are going to plan prior. It is also known as manufacturing planning. It results in an increased output, higher precision, faster turnaround for vital business tasks. It is described as a set of procedures that you follow to have a specific output. So, it generally, what I could say is, converts input into output when we flow through it. So, process planning is my processor in which the input is the design data and as an output we communicate to machine tool and production control. In the production control, there could be scheduling, there could be routing, certain activities are there. If I try to list those activities, I will definitely start with routing. That is, we make certain documents that we call it operation sheets or route sheets that let us know that how the specific job would be manufactured. For instance, if you need to manufacture maybe this pen stand, it has a top body, has a bottom. How would this be manufactured? This is an assembly of two components. These two components would be manufactured separately on an injection molding machines. Then these would be assembled. For assembly, there would be a different setup of the machines that could do it. So, these steps would be first two components are manufactured. The next step is the assembly part. So, this is known as a route sheet. So, we have operation sheet and route sheet, which has different headers such as the serial number of the job, the department from which it is coming, the operation number or the job number or the specific operations that are to be carried on the job, the machine that is there, tools, jigs and fixture which are required for the machines, that will also come. Then time per piece, date, that is the start date, end date, start time, end time, these all could come. Along with routing, we have processes. When I say processes, it could be any of the processes that is the machining processes. In the additive manufacturing, it would be the printing processes. What kind of printing are we taking into account, that we will discuss in the coming lectures in this week only, that additive manufacturing technology and the processes. In the general processes for manufacturing, I could say different machines. For the rectilinear jobs, it is generally milling or maybe shape tools is there. For the curvilinear jobs, we also do some milling, and also lathe is also kind of a milling operation. Some people consider it just as a kind of milling operation where we only control the rotary motion. So, with what processes are there? Then we have the process parameters. Process parameters, if I say, it could be surface finish. Majorly the time is the parameter that is focused upon, that is what time it is taking for dealing, because time is money, that is what is called in a business. So, lesser the time it takes to produce the products to the confirmed quality, the more would be the production or throughput, more would be the profit. So, process parameter, time is one of the major parameters that is taken into account. Then we have machine tool selection. Machine tool could be any of the machines that conforms or that could work on the processes that you have here at the second point. With machine tools, we cannot miss to have fixtures or jigs. Now, operation plan sequence and summary of the process plan is made that helps us to execute it, to take it to the machine tool and the production control, in which schedules are also made. Scheduling, I will put it as here. To put it in a nutshell, I would say the aim of the process planning is to identify appropriate supplementary information from the drawing to aid the processes. That is to have the dimensional information, the geometric information from the drawing or the design, and try to communicate it to the machine tool and try to have the final output out of it. So, process planning helps us to communicate the things to the machine tool. Nowadays, that we talk about is known as computer aided plus process planning. The computer aided process planning or CAP is something that goes beyond the production control even. That means, because computers are involved these days, now we do something known as the factory simulation. Though the name is process planning only, but if I say a word process simulation, process nowadays is more typically used a word for the machining processes. If I say process, that is for manufacturing a specific component. If I try to have a computer aided engineering, that is the final element analysis over it, that is known as a process simulation. For this process, what would the simulation, how would it work, or for the specific machining, how would it work? This is known as process simulation. That is the process planning helps us to do. In the factory simulation, we can even simulate how do we schedule the machines? How do we put machines in a layout? At what distance the machine could be put so that the material travels from one point to another, and where do we keep the material, the work in progress inventory, then who would operate it, all this is taken care. This is also known as plant simulation. Siemens is a company that took a major lead in it. Being a little out of the scope of this course, this could be taken in the coming courses, that would be an extended courses to the present course only, where we will discuss the product lifecycle management, we will talk about the plant simulation softwares and how does these help in a present day life to make our life easy in a manufacturing concern. So, majorly in a computer aided process planning, the factors that help or that affects the process plan selections are the shape of the component or the product that you are trying to produce. Then we have the tolerances. We have along with shape the size of it. For instance, if in 3D manufacturing, if you need to produce a big size of a print, maybe we have a machine of size of about envelope 1 meter by 1 meter by 1 meter, such a big component as a one piece. In additive manufacturing, that is possible. Or would you like to manufacture the components in 2-3 different parts and try to assemble them? That is more important when we consider the design for maintenance. For the maintenance, sometimes you manufacture the components so that you can replace them easily, you can maintain them easily. So, modular design is more taken into account. Size of the component is also one of the important factors that helps you to plan the process. Then surface finish, the material type. This is the kind of the material or the product that you are trying to work upon. We can also have quantity here. When you are talking about the schedule, or the routing for that, here urgency I will put as one of the points, that what is the priorities that you set for the product. That is generally first in first out option that you try to follow, but sometimes some products are required urgently to complete some other assemblies or so. So, then this becomes a more important factor. Then the value that product is offering you. Then the manufacturing system itself. So, this is the process planning. Now, when we talk about the shape, size, tolerances of the product, we always have to consider the part that we are trying to manufacture. That is, we need to have a part drawing with us. The part drawing has the geometrical and dimensional information. Here comes the role of the part programming. Now, to integrate the CAD and CAM, computer aided process planning plays a big role, and to increase productivity and reliability in an increasing competitive market nowadays, this integration is imperative. This is something taken into an umbrella of computer integrated manufacturing, where we have computer aided process plans, we have flexible manufacturing systems, where CAD, CAM, production management or automated assembly, all they come into a single channel and try to communicate with each other. The achievement of a true computer integrated manufacturing system is a challenging task, because CAD and CAM data are heterogeneous and incompatible though neutral files helps you to transfer the data to the machine tool, but to have the data for the production control as well, you need to understand the data in a better way. So, sometimes the geometrical data that is stored in a CAD database is of no use to the production management directly. On the other hand, the data related to the production management sometimes is no use to the design department, those all go in different directions. So, that is why I need to have a common system that tries to integrate them. So, that is what we call as the computer integrated manufacturing only. So, to meet a challenge to have a centrally integrated SIM database, we need to have an attractive practical link between multiple standalone CAD and standalone CAM a communication between them. Now, the linked SIM system would rely heavily on the communication software that links these hardware, mainly the computers. So, with the advent of internet, intranet, and extranets, we have solved many of the networking problems nowadays, that is the communication protocols at the software level, such as we have the programs or the formats such as IGES, STEP or many such have achieved a similar success. Now, we have a crucial step in CNC programming that helps to communicate between the machine tool and the design. Here I said design, I could also say my drawing. So, now not only the neutral file would help us to do it, the post processor also needs to understand something, and it needs to convert the drawing into the final usable format. Now, this is somewhere we have geometrical entities of the part which must be ordered properly, and the numerical control information must be pushed on a separate layers. So, imposing these requirements on the generation of engineering drawing enables the automatic generation of the NC programs. When a program, that is a numerical control, is taken using a computer, that is a computer numerical control. When I say NC, it is just a numerical control which is generally taken using a punched tape or a magnetic tape. Or this is the challenge where we need to have to work upon the part programming. And in the part programming, the first thing is we need to develop the CAD data for CNC or NC. That means an engineering drawing that looks fine from the drafting viewpoint sometimes is not completely something that could be used. That is, NC packages include translation routines that automatically format the drawings and convert them into the usable form. And we prepared the drawing for the programming for successful, what we call it as electronic linking. In this, a few points I would like to jot it down here are: part data should be precise. Which means the coordinates must be accurate before the drawing is sent to the NC package. The accuracy of data is actually used within a round off of the truncation of the errors of the computer running the CAD software. For instance, if I have a tolerance of about maybe 100 plus minus 0.5 millimeter, This is I am giving a binary tolerance here. So, here the nominal dimension, if it is stored, it has to be 100.000. If the nominal dimension is stored, that nominal means the central dimension for the tolerance, if it is stored as something maybe 100.02 or something, this is not acceptable. Yes, 100.001 is okay. So, that is the part data should be precise depending upon the precision that we are trying to get through our program. Now, second is, now since the tolerances have to be given properly, the drawing tolerances should match with the manufacturing practice. Which means in the practice, if the certain dimensions are given based upon certain standards which are there, and we need to take into account certain allowances such as material deflection, such as the cutter wear out, all these tolerances, all these allowances are to be taken into account when we are trying to give the specific tolerances here. That is the work tool combination or matching. For instance, we need to give certain allowances for different kinds of the tools sometimes, or different kinds of the jobs that we are using. Maybe the cutter, if we have the specific work tool combination. For instance, if I need to grind a mild steel workpiece using an aluminum wheel or maybe from a ceramic wheel, the aluminum wheel will wear out faster. So, for that tolerances are to be given, or different work tool combinations are there for a harder workpiece. For example, maybe high speed steel workpiece has to be then grinded. It could be more useful to have a ceramic wheel only. So, it depends upon what kind of combination do we have. So, this is an important point that is considered. Then separate drawing annotations from the drawing data are to be given. Which means we place the annotations, that is the notes and dimensions and data, that is the geometrical entities, on different layers. That is why I put two letters there, G codes, M code. What are those? Other than G and M, we have N, C, other kinds of codes as well. These are all different layers for to put annotations, to put the machine information, to put the geometric information. So, all these were put through the different layers in a code. In a code, when I say it is a communication language for the numerical control or computer numerical control. Now, an important point here is that the profile entities must connect. Which means a typical machine tool will cut continuously only within maybe 0.0001 centimeters. So, these entities should be connected in a way so that within this tolerance, maybe say 0.0001, I would say millimeter. So, therefore, it is important that CAD databases meet or exceed the machine tool accuracy. Now, dimensionality requirement must be specified. So, we need to have an order, that is why we do call it as routing there for the manufacturing input. Order the manufacturing. Which means the geometric entities should be input in an order, they are connected to each other. Maybe it could be clockwise or anti-clockwise. The path has to be unidirectional that the cutting tool might follow. So, these require the designers to enter geometry in a manufacturing order, so that they could have good creativity and productivity in their designs. But this part is my CAD data or my design. This has to communicate with the other part which is my machine tool. Now, since the NC program is a combination of the machine tool code, we have a program here which is machine tool code, machine specific instructions, then we have geometric information, we have with us the motion statements, and we have the different input parameters such as cutting speed, feed, or we call it some auxiliary functions or so. When I say parameters, these are machining parameters. Now, the machine tool code and machine specific instructions would be definitely depending upon the kind of machine tools that we have. Here we need to have a good description of the machine tools. That is, we need to understand that the machine tool has a central processing unit that is known as MCU. MCU, which is machine control unit. Machine control unit, that is one which is connected to the machine, which controls the machine. It is also known as the controller unit, or maybe the controller only as a short. People call it controller. So, it is the brain of the machine which reads the part program and controls the machine tool operations. It is not a single unit, it majorly has two functions, that is DPU and CLU. DPU is my data processing unit, and CLU is my control loop unit. The data processing unit reads and decodes the part program statements and processes the decoded information and provides the data to the control loop unit. The control loop unit receives the data from DPU and converts it to a control signals. The data usually provides the control information such as new position of each axis, its direction of motion, velocity, some other controls. So, CLU instructs the DPU to read new instructions of the part program and control the drives that are attached to the machine lead screws and receives the feedback signals. So, CLU I would say instructs DPU control drives and receive feedback. Each axis of the machine could be set in a different kinds of the axis or different kinds of the capacities that it could be moved or the kind of the motion that it could have, that is 2 axis, 3 axis, 4 axis, 5 axis machines could be there. The robotics which are not using the Cartesian system, we have the robots which are working in the polar coordinates, that also work in the 6 axes. So, or different degrees of freedom are given to them. So, to design the machine, each axis has its own lead screw, control signals and its feedback control. So, that is for sure, because each axis has to move independently, that is how it goes. So, this becomes our second part of the machine tool characteristics, that is the axis of the machine. Axis or motion of machine tool. So, because workpiece is machined to a finished shape by allowing a relative motion between the workpiece and a cutting tool, this relative motion is providing by either keeping the workpiece stationary and try to move the cutting tool over it, or sometimes the tool is stationary and workpiece only moves. This relative motion is known as the motion of the machine tool. This motion of the machine tools can be into different axes, as I said. It could be 2 axes, it could be 3 axes. With 2 also we have 2.5 axis, it is plural AXES. We have 4 axis and 5 axis machine. So, in NC machine tools, each axis motion is equipped with a driving device to replace hand wheel of a conventional machine, because in the conventional machine, suppose drilling to be taken, it is a hand wheel that helps us to do the drilling. In NC machines, it is a drive or a motor drive or some mechanical or hydraulic drive that tries to drive your drill down to do the drilling. So, a driving device may be a DC motor. Axis of motion is defined as an axis where relative motion between the cutting tool and workpiece occurs. The primary 3 axes x, y, z are there. So, I will just put these axes here. Let me say I have a workpiece with me. So, we have in the x direction, y direction and z direction, x, y and z direction. So, we have 2 axis machines, either the bed of the machine or the tool moves in a single plane. It can move in x direction, it can move in y direction. It can control both the drives together to have a diagonal movement as well, but it moves in 2 directions only, 1, 2, x and y. In 2.5 axis, this third axis is independent, it cannot be controlled together with x and y, but bed can move in 2 directions, x and y, and also it can be set into a third direction, that is z, that is 2.5, which is controlled or which is manually controlled, right. Then we have the 3 axis machine in which x, y and z, all of them can be controlled together. That is, my point can move not only in the planar motion from one direction to another in an angular way, it can also go to a diagonally into 3D space in any way. So, that is why we get the third axis here. In a 4 axis machine, on the top of these 3 rectilinear motions, there is a rotational motion as well. For instance, the bed can move in x, y and z direction and tool can also rotate. This is 4th axis. In 5th axis, maybe the workpiece can also rotate. There could be 5th, 6th axis machines as well. So, this is the machine tool description on axis motion that we have different kind of here in the machine tool. Also, we have 2 kinds of the machining. Machining type. Number 1 is point to point, number 2 is contour or continuous. When I say point to point motion, the machine moves from one point to another point, that is from one point to another point my tool moves. This is point 1, point 2. So, maybe to cut a square or to cut a rectangle, it will move from point 1 to point 2 to point 3 to point 4. point 3 and point 4 on this plane. So, point to point it will first move, the second point, third point, it will keep on moving. For each movement it will consider it as a linear motion between 2 points, that is, it draws a line segment. In the continuous or contour machining, it will start from one point and try to make a curve. So, this is contour. The starting point and end point is all same. I will call it as C. So, machine tool can perform these two types of the operations or two types of machining, the point to point and the continuous. Point to point machining is a simplest type of machining. So, the obvious example of this is drilling a hole at one point, then going to other point, drilling a hole at another point. All these things are taken, and when we write a G code, when we try to develop the decision support systems, the machine nowadays always understand by itself, the systems are automated, but we need to understand whether we are working with a 2-axis machine or we are working with 3-axis machine. If it is simple drilling machine, the point to point is only the type of the process or machining that it takes. The exact path of the tool is followed by moving from point to point, immaterial of assuming of the time whatever it takes. So, tools should not collide or the workpiece should be holding fixtures properly. These we will discuss when we will talk about the certain tool path verification. In the tool path verification, we also see whether collisions should not be there or the double movement of the path should not be there. Also, it is important to understand that there are 3 kinds of systems in the machine tool. It could be a numerical control, it could be computer numerical control, it could be distributed numerical control. When I say numerical control, as I just discussed, it is just a machine or program that is stored in a CD or it is stored in a system other than a regular computer. But nowadays whatever we have is the computer numerical control machines, but the base is only, the GUI is only the numerical control machines. This is analogous to, now we have Python, now we have Anaconda, different kind of languages that you try to work, and in the MATLAB you have different modules to work upon different kind of languages. The base is generally the C language that you have learned. In this case, we are trying to learn the NC program that helps us to take decisions in the computer numerical control and the distributed numerical control. Now, computer numerical control is simply a numerical control where computer tries to control all the system, and the feedback since information is also generated by the computer numerical control, and that is taken by understanding different variables such as machine downtimes, the work in process in the machine, the production rates, scrap rates, and some other production data that goes as a data input in my production scheduling as well. On the other hand, we have here is distributed numerical control, in which a central computer is there to which group of CNC machines are connected, because if separate CNC machines are to be put the data into, for each of them the data or the process would be taken as an individual process. Or for instance, if I have installed 4 exactly same or similar machines, let me say MCO 250 drill I have installed, 4 machines are there, for each of them I have to operate them and put them the data together. In a distributed numerical control, I can make a one program that to put workpiece at the specific location in the work table that I have and try to give a single program to all those machines. So, this is distributed numerical control. So, communication in a distributed numerical control system is usually achieved by using a standard protocol, that is we use general the TCP IP, using the internet facility that we have, or maybe within a program or within a system or within your server, it could be an intranet program itself. So, a central computer has various functions, that is it stores NC programs, it downloads these programs to any number of CNC machine tools, it performs the feedback task for them, it provides communication between various components of the overall distributed network system. So, major advantage of the distributed network system is that it can be centrally monitored. It is very important when we are dealing with different operators, when we are dealing with different working shifts, and when we are dealing with different kinds of the machines. So, DNC is the one of the systems that we work upon. So, that is what we call as overall when we use TCP IP systems in conjunction with the recent Internet of Things or Industrial Internet of Things, we call it as smart manufacturing. it is too narrow a term at this point of time to discuss, because we are majorly talking about the GUI of the part programming that we develop for a CNC machine. So now I would like to take a small halt here and meet you in the next part of this lecture, where we will discuss the part programming features and how do we actually design a G and M code. Thank you.